Okay, let's start. So, welcome to EDEC Business School. I'm Frederic Blanc-Brun. I'm the director of the EDEC Infrastructure and Private Asset Research Institute. And today we're going to talk about a new paper that we just released called It's Getting Physical. And as you might have guessed, it's about climate change. So, by way of introduction, I'll just give you a very brief overview of who we are, for those who may not know. EDEC Business School has done a lot of research over the past 10 years on infrastructure investment. It started in 2012, so more than 10 years. The EDEC Risk Institute, which has now become the Climate Risk Institute. Our colleagues with whom we also work on these topics, including modeling, which I'll return to. Since 2016, we've been EDEC Infra. We've done significant amount of work on the valuation and the risk and the performance of unlisted infrastructure investments. And since 2020, the same group of people has also been involved in the commercial distribution of indices that were created on the back of the technology created by EDEC Infra and all the data collected by EDEC. Now, for a few years, we've also been working on climate risk and climate change topics in relation to infrastructure. In particular, this is our main interest, to what extent climate risk impacts the valuation, the risks, the priced risk of infrastructure investments. So with this new paper, we wanted to ask two very simple questions. What risk does climate change create for infrastructure investment before 2020? Now, the reason why we're asking this question is because it's often the perception that until 2050, before 2050, and that until 2050, it's often the perception that climate change isn't going to be that bad. The consequences of climate change aren't going to be that significant. And therefore, well, maybe it's not that much of a worry. And I think we wanted to challenge that notion because we could see in the data that it wasn't necessarily the case. But it's not very easy to detect. So we'll show you how we do this. And another related question was, are those risks to infrastructure assets because of climate change material in developed economies? Again, often received wisdom or received the idea that only certain parts of the world will be negatively impacted by physical risk. But actually, infrastructure is mostly, especially investable infrastructure, is mostly developed economies. And therefore, it's possible that if these risks are material, investments in developed economies might be very effective. Right? So two very simple questions, which we embarked on, in fact, a couple of years ago when we launched this research program on infrastructure and climate change. So what I want to do today is take you through 4 different topics to try and answer these 2 questions. First, it's always good to define your terms. So I will go back to what do we mean by physical risk? It's not necessarily a notion that's well defined and always well described or spoken of. And therefore, it's kind of useful to return to what we mean by physical risk in the context of climate change. Then we talk about how to measure what we call the baseline. What is physical risk of infrastructure assets today, which requires very detailed, very granular data, and a very technical knowledge of individual assets. And then we'll look at what that looks like in the future, how these exposures in the baseline today to climate risks, how they pan out in what we refer to as the hothouse scenario. I will come back to what are these scenarios until 2050, see what the impact might be on different types of assets. And finally, we'll consider what that means for investors, because investors in infrastructure assets aren't exposed to the average asset or all the assets. They are exposed to some infrastructure assets, and not always a lot of them. So there's an element of randomness in their exposure to physical risk, to climate change, which is interesting because it may not be something that all investors are aware of. So this leads us to some interesting conclusions, including one of our headline conclusions, I'll give it to you now, which is that in some cases could lead up to or more than half of the value of your portfolio before 2050. because of climate, because of physical risk created by that. All right, so first, let's return to what is physical risk. What do we mean by physical risk? Because after all, you might think that, okay, sometimes there's a storm, sometimes there's a flood, extreme weather happens from time to time. What's the problem? It's been like this for a long time. And so that it's important to understand that this isn't really our concern. What we mean by climate change, of course, this is a very short definition of climate change, is not just the weather. It's the result of the global increase in temperatures, which is itself due to the higher concentration of greenhouse gas in the atmosphere, right? Which we can picture by looking at a chart like this, with many of these, which represents as these representative concentration pathways, so the R's and P's for different levels of heating, of forcings as it's known, of the atmosphere and of the planet, of the surface of the planet. So the numbers that goes with the R's and P's are in watts per kilometer square. And it's basically a measure of how much energy and therefore how much heat is created and added in this case. So this is by relative difference, relative reference to a baseline temperature. And so here you see that in the most, let's say, the best scenario, the least warming scenario, we still have from 2000 to 2100 a fair amount of temperature increase, and of course in the worst case, or not necessarily the worst case, but one of the bad cases, a lot more average temperature increase. And if you stop at 2050 here, so let me just show you a little bar here, 2050. You see that we're here around 2024, 2025. Okay, so you can see that there's still a whole lot of, even in a less dramatic case, the blue lines, the RC 4.5, still a whole lot of increase in temperature to come. Okay, so that's what, of course, is meant by climate change. And the problem here is that it is changes in weather patterns. So it's not just the weather, it's more weather, more bad weather, more frequent and more extreme weather. And these events are typically, in the most common cases, floods, 44% increases for the past 20 years. These extreme weather events have been floods. In 28% of cases, they've been storms, and in 6% of cases, this is the third most likely case, it's been extreme. And then, of course, there are other phenomena. But the point here is that these are the most common and therefore the most likely to become more frequent and more intense extreme weather events. And as it happens, these are the events that impact infrastructure assets the most. This is why we're interested in it. Because we already know that over the past 20 years, the occurrence of this type of event has more than doubled in the case of floods and increased by 40% in the case of storms. So what that means is that, yes, there's extreme weather from time to time, but the phenomena that we're looking at means more extreme weather and worse. This is important to set at the onset, because it allows us to think about this other question, which is, well, okay, infrastructure is usually quite robust. It's built to last, it's steel and concrete. And so we should be able to withstand bad weather. But if this weather gets worse and worse, and if this bad weather gets more frequent, of course, this can still have a material impact. So floods can destroy assets, it can create revenue loss, because you can't move the asset while it's doing it. They are costly in terms of operating expenditure, capital expenditure. Storms have pretty much the same effect. So this is a road in California, this is a wind farm destroyed by a storm in Greece. And heat doesn't destroy things so dramatically, but it does destroy things. It creates needs for the maintenance. This is a railway in Australia. By the way, I'd check none of these are fake. So this is a river. And heat in particular would reduce the asset life. It require maintenance and replacement of parts more frequently. So all these things can have material impact on the performance and operational performance and the financial performance of the infrastructure assets. And so when we say climate change, physical risk, we mean more frequent, more damage. Okay, so while current assets may be built to withstand current weather conditions or the weather conditions that were envisaged when they were designed, it means that the business case that was attached to this project did not necessarily take into account more bad weather in the future, right? So future revenues, future costs, expected profits, future dividends in any given project will be completely predicated on the current climate or whatever historical climate was envisaged at the time. So the cost of capital of these projects is also predicated on the current climate, right? So what that means is that this evolution, this more frequent occurrence of worse weather that has a material impact on the assets, is unlikely to be priced in. And there are two reasons for this. One, well, there's two reasons to argue this, rather. One is that when we look in the data, we really struggle to see any kind of effect of these climate risk exposures on the cost of capital of these companies. But also it makes sense because these changes are uncertain. It would be very difficult probably to include them in your business case without becoming uncompetitive. So in order to win a bid, in order to win a project, you build an asset on the basis of the weather today. But the realization of this risk is likely to be very material because for the reasons I just gave you, these risks will impact the cash flows of the assets, the future dividends. They will also impact, come back to this, the discount rate, the cost of capital of the asset. These two components, of course, put together, give us a net asset value, and the discount rate for the future cash flows is the net asset value of the investment. And if they're both impacted by these events, we may have some very material effects. As a final example here, I have, that's a wind farm that is on fire because it's hit by lightning. Now, you might think, well, people should have thought of that, and they do. So wind farms, wind turbines have like sensors at the tip of their blades so that if they're hit by lightning, the whole structure is grounded immediately, and the lightning doesn't affect the structure, except it doesn't always work. So every now and then you get wind turbines like this that are destroyed by storms. So again, if you have more storms, if they are more intense, these events are going to happen more and more often. And so that will materially impact future business prospects and the riskiness of that particular kinds of projects. Of course, it all depends where they are. Now, I wanted to point out something before I go into our methodology, which is how not to do this, how not to measure physical risk. This is how what unfortunately is still, when it's done today, it's often done like this, which is to find a point on the map where your asset is supposed to be. Then overlay some hazard data on top of it. So for example, some flood data. So this is a road. Say, okay, well, the flood data says that this part of the road is red and this part of the road is orange because there's less flood risk. Then make a score and add that to your TCMD report. Press send. That's what a lot of people do. Once you've done this, can you answer my question? What is the impact of physical risk on infrastructure investment? No, you can't. You can't because you have no granularity. And I'll show you that granularity is very important to really pinpoint what risk an individual asset is exposed to. You have no scenario, you have no forward-looking information. So you're not really measuring climate change risk, right? What the risk that climate change is bringing to your asset. And you have no valuation of your risk, just have a score, which frankly can be calculated in different ways by different people, so it doesn't necessarily mean very much. What we want is to know, what is the dollar value of the risk in a scenario that, for example, implies a lot of climate change by 2050 for an asset that is very precisely defined, okay? And that's because physical risk impacts these assets in a very specific way. It only rains in a certain place, for example, and 100 meters further, there's no flood. So in typically. So depending on all sorts of factor considerations, including elevation, for example, and also the type of asset being impacted by it differently. So all these things, if they're not taken into consideration, if you do this, you haven't done much. Maybe you've ticked the box in your thesis, therefore that's the bad. Okay, so at this stage, I want to introduce the notion of, briefly mentioned it in the introduction, but I want to introduce the notion of baseline versus scenario a bit more clearly. So what we call baseline is now the baseline physical risk data is what we can tell about the exposure of infrastructure assets to weather today. So for instance, this is a road that was flooded in India in 2015. This is an airport that was flooded in the US in Fort Lauderdale earlier this year in April. And that's one thing. And that's usually most of what the information that people had about their assets. And in a way, it's a bit it's not that interesting. First, if you own the asset, you probably have looked at insurance against catastrophes, and therefore you know this already. But also, that's not climate change, that's now. Not climate change, and the risk created by climate change is just the weather. Okay. What we want to know is what happens tomorrow. What happens so this is not an actual flood event, so it's an artist's impression. So this picture is fake, that's the only fake picture I have today. But it shows the Houston airport. If there was a flood, a massive flood, much more massive than we have today, as you can see that the planes are much more underwater than they were in Fort Lauderdale in April. But that's what we want to know. How is this going to happen? How likely is this to happen, and how much will it cost? Because this is happening today. This is an insurance question, not a climate risk question. Okay, so what better approach can we propose than what I showed you earlier? First, we're going to consider a large number of infrastructure investments that are representative of a global universe in which investors invest in private infrastructure. That will help us to have results that are that speak of what this market is like and from which we can extrapolate. We're going to establish a baseline again, so exposure to extreme weather today, in a very granular manner. I'll show you how we do this. Then we're going to consider one climate scenario where there is a lot of physical risk. There are many scenarios. We'll take one, which is the one in which there's the most physical risk by 2050, so the least decarbonization, of course. And then what we'll do is that we'll project the cash flows and the valuations of each one of those assets in this scenario to take into account the impact of the scenario and of the exposure of each asset to physical risk, because each asset will have a different exposure on the future cash flows and the discount. In other words, we're going to do a DCF in the future in a scenario where the economy doesn't decarbonize and there's more and more bad and frequently bad weather. Okay. And finally, we can use these results to measure what I've called the pure impact of physical risk. I'll come back to this, but in a nutshell, once you do this, you've picked up two effects. You picked up the effect of the scenario, because the economy is supposed to follow a certain trajectory in this scenario. Therefore, the revenues of the firm, the interest rate, etc., inflation follow a certain path. These scenarios are all macroeconomic projections in the end. But the impact of climate change is very much specific to the asset and whether it can be flooded or not, etc. So we'll separate the two to make sure that we only look at the impact of physical risk and not just the impact of the scenario, which is a broader question, right? And finally, once we've done that for hundreds of assets in a representative setting, we'll look at the implications of these findings in a context where infrastructure investment portfolios are quite concentrated. So we've looked at the data as well. I'll show you the review we've done. But most infrastructure investors have between 5 and 20 assets, which is not that many, or in a fund, right? Fund managers have several funds usually, so they have more than 20, but they may not have more than 20 per fund. They won't have more than 20 per fund. So the fact that you have risks here which are clearly very specific to the asset, mean that if you're not diversified with a very large pool of assets, then you may be exposed to very high physical risk already. Okay, so let me show you the data that we're using. This is just a very brief outline of what goes into this analysis, which is basically what we call the infrastructure reference informametrics reference data set, which is what we use in informametrics for various purposes, including producing indices, etc. But today we're going to use this data to look at climate risk. So what we do is map out an investable universe across 27 markets, which are all the major markets where you invest, which corresponds to about 9,100 infrastructure companies, private infrastructure companies that you can invest in, that are privately invested. We estimate at the end of last year that this represents roughly $4.1 trillion of enterprise value in market fair value, market capitalization. And then we track in great detail 20% of that universe. So we have a representative set of this whole universe, which is of course combination of sectors, business models, etc. If you know your TICS taxonomy. And we track 20% of that universe, and that represents, on the equity side, roughly 410 billion of equity market cap. Okay. And that's also about 700 companies. So we're going to have information on 700 companies. This is extremely detailed. We can price them every month to produce the informametrics indices and other data. And here we're going to price them in a climate scenario, given their exposure to climate risk. First, we need to figure out what their exposure to climate risk is, right? This is just a bit more detail about the sample, how it's this universe, how it's organized by sectors. So again, here you need to know your TICS codes in order to read this chart. This is transport, this is utilities, this is renewables, power, digital infrastructure, and this is water and energy resources, or pipelines, really. And this is this breakdown by the same universe broken down by country, and again weighted by market capitalization, so the market value, the fair market value of equity. Okay, so this is the data that's going to go into this analysis. So we can already say that the results are going to be representative of what infrastructure is like. Now, let's see how we might know what the baseline of these assets, the exposure today, is. So the first thing we're going to do, instead of putting a point on a map and looking at the color, that's what other people are doing, we're going to produce a very, very granular assessment of the exposure. So we'll take the assets. So this is one example. Here you have an airport. You have every little nooks and cranny of terminal, every bit of the taxiway, every runway, exactly where it is, how wide it is, etc. So we'll have a very high precision in terms of what the asset is and where it is. And then for each one of those bits of assets, basically, we'll look at different hazards. So for instance, flood, which is probably the most important one, storms as well, and heat. And we'll look at what we call a damage function. This is a standard process, especially in the insurance industry, which basically is a mathematical function which tells you, depending on the amount of bad weather, so the amount of flooding or the amount of the strength of the storm or whatever, how much damage is caused by to the asset. And of course, this function is a function of the asset. A road or an airport are affected by flood differently than a wind farm, which is affected again differently than a pipeline, which probably isn't affected very much, etc. So we use 34 different types of damage functions, which corresponds to different TICS categories, so to different types of assets. So that when we say, oh, there could be a flood here, and this is, by the way, the flood model is a 30 meter by 30 meter resolution model, so it's very precise. We say, well, this bit of the runway can be flooded, and what the model says is that there's 1% chance that this will be flooded with 3 meters of water, for example. Depending on depths of the blue, there's more or less water. There's a 1% chance that there'll be 3 meters of water on that spot, and that will cause X amount of damage to, in this case, a runway, which is different than the amount of damage it would cause to a terminal, because it's a different sort of thing. Right? So here you're getting into something that's very precise. And what's beautiful is that we managed to industrialize this so that we can apply this to hundreds of assets. In fact, we can apply this to any asset you want on demand. So you're going to have a very detailed idea of how much damage different extreme weather events can cause. All right. And we can compute a percentage of the asset that's impacted by a certain event, by a certain extreme weather event. And we can tell you what the financial value of that is today. If X% of this airport will be impacted by this flood with a 1% probability, that's probability of the flood, then that's the value at risk, effectively the 99% value at risk. If you times this by either the book value of the company or its market price, depending on what you're looking for, you get a 99% value at risk given the type of hazard that this asset is exposed to. Right? So you can do this for many assets. Just to give you another illustration, so we're in the UK, so there's a Birmingham airport. And here I've showed you two airports, but actually, we do this for all types of assets. You have your outline of the airport, then every little different bit. You have the damage function. These mostly come, by the way, from the engineering literature, or we don't make them up, huh? Or they come from, for example, for flooding, they often come from the Netherlands, the Dutch government, because there's a great deal of knowledge in the Netherlands about flooding, and so they produce this kind of information. So this is in the literature, but this is quite technical literature combined with this information and your flood model. You get something like this. So we have a 1% chance here, 1 in 100-year probability that this airport will be impacted by flood. Damaged by a flood. 77.8% of the airport will be damaged by the flood, which represents a physical value at risk of about less than $69 million. Which is also, you can also calculate an expected loss, of course, is the probability. This is probably roughly the price of insurance. That's today, okay? All right, so, okay, why do we do this? Why do we go to the bother of doing this? Because after all, why not? Look at a map and say, this is red, this is blue, so this is green, and so this is high, this is low, and leave it at that. I'll show you an example why this actually works. We did a little test of this approach earlier this year. There were floods in Italy, as you may have heard. There were very bad floods. It was 1 in 200-year event. A lot of rain, but only in a very limited number of places. So on this map, you can see the flood model, which is the black. So this is Ravenna, south of Venice. The flood model, which is the black shaded area, this is where you can have a flood with 1% probability, 1 in 100 years. And the blue color is the actual flood, which was detected by satellite, and we can map overlay, right? So what you see here is that this flood, again, was very specific, right? It's not even all the areas that could be flooded were flooded. Where there was a flood, it was very bad. So what we do is that we take the actual flood instead of the flood model. In this case, we apply to all the roads in that area that we know, because we have a map of all the roads, and we look at what the replacement cost might be, just to try and see what the impact of the flood, quantify the impact of the flood in euros for the purpose of kind of validating the model. Because of course the Italian government did the same thing. They went out and looked at all these different roads that had been destroyed or damaged by flood, and they came up with their own estimate. And we can actually agree with them. It's roughly between 100 million and 120 million euros just to repair the roads in those areas. It doesn't sound like a lot, but actually it's a very small area. So that's not the point. The point is that the model managed, with this damage function, managed to really capture how much damage had been done. And as you can see, you only know this if you're very, very, very granular, because if you were just pointing at a big square in your road was here, but the flood was there, well, there can be a flood, really bad flood, and your asset would not be affected if it was over here. So you need to be very precise. Precision matters a lot. And if you don't use the right kind of hazard model, if you use an approximate location, you don't know that much. Really, you're wasting your time. Don't even try to measure physical risk like this. All right. So the conclusion from this part is that physical risk is highly asset specific. We're not going to be able to broad stroke averages saying physical risk is like this in this part of the world and like that in this part of the world, and these assets are like this and these assets are like that. It's not like this. This is extremely asset specific. You need very precise data to understand what the impact of floods, storms, and heat is going to be on the asset. And the way these floods, these storms, etc., will impact the assets also requires a very asset type specific damage function. You can't just say, oh, there's a flood, so this part can be flooded, so the damage will be X. Depending on the type of asset, it will be a very different kind of damage. You also need very specific information to understand the damage. And that leads to the impact of extreme weather events, again, being very, and therefore the exposure to physical risk to be very highly asset specific. Okay, so that's great. It's super interesting. Of course, all our team had lots of fun developing all this, because who doesn't love GIS data and maps and all that kind of stuff? But that's actually not enough. It still doesn't answer our question, which is what's the impact of physical risk on the value of your portfolio. We still don't have a forward-looking view, because this is today, and we don't know how much it will rain tomorrow, but we can try and use climate scenarios for this, and we still have no dollar value. We haven't valued these risks. Okay, so while this baseline data has to be very granular and is necessary, it's not sufficient to measure physical risk in infrastructure. Okay, so now let's look at how we're going to take this to the next level and project it in the future. In order to do this, we need some scenarios. All right. So the typical scenarios that are used today that we use in this exercise are the NGFS, stands for the Network for Greening the Financial System. It's an organization that a club of central banks, prudential authorities, and international development organizations who work together to try and transform the IPCC temperature scenario into what are in fact climate policy scenarios. So they come up with different policy options. You can have, for example, high carbon taxes and an orderly transition. You can have high carbon taxes later and have a delayed transition, or you can have no carbon taxes. And of course, carbon taxes here is kind of a proxy for everything you could do to decarbonize the economy, and get a very different kind of scenario with more physical risk and less transition. So today we're going to look at this because what we want is this scenario, the one of current policy and no transition or hothouse family of scenarios, which means that actually this isn't the most pessimistic of scenarios. It's a scenario that implies that we stop reducing emissions from now. We just stick to current policies. It doesn't really imply that emissions continue to increase a lot, which could be the case. But anyway, that's in this context, the right scenario to use to answer our question. And we stick to the NGFS scenario because these are standard and they're used by a lot of organizations. I have to say that they can be improved. And in fact, our colleagues again at the EDEC Risk and Climate Risk Institute are working hard on that, because there's lots of work that can be done to develop better scenarios and a better understanding of the risk of the scenarios, as opposed to having static paths, right? But today we'll just use this no transition or hothouse, sorry, current policy system scenario. Okay. So in this hothouse world, the current policy scenario, according to IPCC, physical risks are multiplied by 2 by 2050. If you remember the chart I showed you earlier, the temperature, average temperature with the red line was pretty much doubling between now and 2050. So unsurprisingly, you double the temperature, you have at least twice as much physical risk. And then of course it gets a lot worse, which is usually again the picture people have in their head. Until 2050, it's not going to be too bad. But after that, it can get a lot worse. So and the other important thing is that how are these baseline risks that we've looked at going to change, right? Trend is that in this scenario, those risks will pretty much follow this doubling, right? So if you take that into account, it corresponds to about 2.5% increase a year. So a 1% event, which causes a 10% amount of damage now becomes 2.5% more likely. That's 2.5% of 1% every year for the next 30 years. In fact, what that really means is that in 30 years, it has become a 2% probability event. But instead of every 1 in 100 year event becomes a 1 in 50 year event by 2050. And that's in this no transition current policy hothouse scenario. Okay. So that's how the risks are going to change over time, the risk that we can measure now. So if we just look at this, sorry, I had right. If we just look at this for the baseline, we look at the risks that we calculated for all these assets. There's a percentile of exposition to these risks. So this is what I call physical damage at risk. It's the amount of damage, right, created by these different events. Obviously, there's a whole lot of assets which are not really exposed at all. So these different types of events, for floods, for example, or for cyclones or those types of storms, we have a pretty much half of the distribution today has no risk. Meaning these are assets that doesn't matter how much it rains or what kind of storms you get today, they're not exposed. They're not going to be damaged. And then some assets are going to be damaged, but a little bit. A few assets today again will be, so this is a cumulative distribution. A few assets will be impacted quite a lot. And on average, the damage is very low. Big surprise. Today, the infrastructure that we have is built for purpose or for the right purpose. And therefore, when it rains, it doesn't get completely destroyed. It can happen in some cases because you have extreme events, you have extreme weather in some places like in Italy, which is that's very exposed, but most roads would not be destroyed in the least destroyed by the next time it rains a lot, because they're actually designed for this purpose. However, sorry, I have a little problem with my animations here. It completely changed in that. So if we do the same assessment, again, we're not doing asset pricing yet, and we're just looking at the amount of damage. In that scenario where the risks increase all the time, it becomes much higher, right? And so the top of the distribution, yeah, cumulative distribution, basically the top 10% of all the assets are now much more exposed. Sorry, yeah, much more exposed. Some of them, in fact, the most exposed will be completely destroyed by 2050, given what they are today. And because of the change in intensity and frequency of extreme weather events. Of course, these are just a few, right? This is the top of the distribution. Most assets would not be completely destroyed. But look, even the first 25% of the distribution is now 10% exposed to it. It's not going to be 10% damaged by 2050. So first, this is going to be material. There's no question. And second, in some cases, it's going to be so material that it means default and bankruptcy, pretty much, because you lose everything. And again, you have to think about this not only in terms of, oh, every year it's a 1% probability or 2% probability. If you're investing for 30 years, the probability that a 1% probability event happens once in 30 years is actually not that low, about 30%. And if it happens once and the asset is completely wiped out, right? So this is a big change in the picture, right? And it's just by looking at damage and how the damage might change over time in this hothouse scenario. Sorry, I had a, there you go. Okay, so that's one thing. That's just the damage, the amount of damage, physical damage. Now we need to try and price. To do this, we're going to do this in two steps. First, we're going to look at how those damages will impact the financial, the cash flows and the financial of all our companies. And then we'll price those companies. So here I have to distinguish between two things. The first one is in the scenario, what do? I project the revenues, all the cash flows, etc., of that firm on the basis of what? On the basis of the economic trajectory that the scenario implies. So this hothouse scenario, it implies, despite the fact that there's more climate change and more physical risk, it implies some economic growth because the world goes on, business goes on, and by 2050, it's not that bad that the whole economy suffers kind of systematically, fundamentally from physical risk. And so there continues to be some growth, there continues to be some, in other words, some business for infrastructure companies, and they make revenues. And if the economy grows, they should have more revenue. If there's inflation, their revenue should be adjusted, etc. So we want to reproject all of their financials in the future in the context of this particular economic scenario. In particular, the impact on, to the way we do it, the impact on, of GDP, inflation, etc., on total assets. We have this in the scenarios by country. And so that's the impact of the scenario on the value of the firm in terms of macroeconomic effects. But then there are also asset-specific, of course, impacts on the financials that are due to physical risk exposures. For instance, we're going to take our physical risk estimate or damage factor and apply it to different parts of the financials. For instance, we're going to degrade the total assets. We're going to increase because the assets, it gets damaged. We're going to increase OPEX by an equivalent factor. We're going to increase debt because when your asset is damaged by physical risk, you need to repair it, you need more money, you need more capital, or you need to protect it, you need to invest in resilience, which in the end is also costly. So we assume that this is funded through debt. And of course, the revenues get impacted as well, right? Because as we said, if you partly disable or destroy an asset, you can use it less, so the revenues are lower. So we have all these standard financial metrics which go into the DCF formula in the end, the cash flow, the dividend projection, which are going to be twisted or tweaked, I should say, tweaked by this physical risk damage factor that we've estimated for each firm in different ways. Less revenues, more costs, more debt, etc. That's how we're going to both project the financials of the firm and tweak or impact its financials as a function of how much physical risk it's exposed to. Since we now know this and we know how from a baseline, this has changed over time. And then we're going to price the company. So how we do this is pretty basic. We always do it the same way. We compute a net asset value at one point in time, which is a discounted cash flow formula. This discounted cash flow formula implies the discount rate, which is a combination of risk-free rate and a risk premium. And this risk premium itself is a combination of risk factor prices. So you might say the market return for the exposure to a certain risk factor and the exposure of the company to this risk factor, the beta of the company. These, we've presented this many times before, so I don't go too much into the details, but these betas, these risk factors that drive the premium, which drive the discount rate, which drives the NAV, are things like total assets, leverage, profits, etc. So things that are going to be impacted by our climate change scenario, right? So first, the dividends are going to be impacted by our climate change scenario. If we have less activity, less revenues, this is going to impact our future dividend forecast. The macroeconomic part of the scenario is going to impact interest rates because, again, the scenario is a total global equilibrium model. So it includes future interest rates. We're going to take that into account. And then the betas here that drive this risk premium, again, things like leverage, profits, etc., will be impacted by the damage factors impact on the financial. For this number, this is important. What do we use? Because we don't know the market price of risk in 10 or 15 years. We don't know. We can't know. So we assume that in the long run, there is a good old hypothesis in finance applies, that in the long run, the market price of risk mean reverts. So we of course, we know this number for the past 20 years, because that's what we do with Informametrics. We calculate this number so we can price hundreds of companies every month. So we take the long range value for that number and we just keep that. So in our scenario, we don't focus too much on the risk premium for each risk factor. We focus on the change of exposure to risk and the impact that it has on the different steps in the DCF and of course on the dividend. If you do this, what do you find? Okay. So this is where I want to measure the pure impact, the difference between the macroeconomic impact and the microeconomic impact. In a hothouse scenario, again, there's some economic growth, there's less inflation than in the decarbonization scenarios, because there's no carbon tax. And so at the macro level, actually, it can seem like quite a benign scenario. It may even create the impression that there's a little downside to having no transition, at least until 2050. But if you look at the details, it's not that it's not at all like this, because so the pure impact of increasing physical risk we do what I just described. We compute the asset value in the hothouse scenarios with and without the exposure to climate risk exposure. So if I go back to this, I'm going to do this exercise twice. I'm going to do it once without those things, without the damage factor, as if all my infrastructure was completely climate proof. Doesn't matter how much weather there is, doesn't matter how much it rains, no damage ever. I just run the model with the financials, given the scenario at GDP growth, inflation, etc. But I ignore the effect of climate risk. And then I do my DCF, same thing. All right. But again, there's no impact on anything, because it's as if there was no impact. So once I've done this with and without the effect of the factor, I just need to take the difference between the two, and that gives me the pure impact of physical risk on infrastructure assets, just the impact on the NAV of the exposure to these risks. Because the scenario, after all, I'm less interested in. It's interesting to compare scenarios, but here I'm looking at one scenario, a scenario that you may or may not believe in or be interested in or find relevant. So I've removed the effect of the scenario. Okay? And if I just look at this difference, the pure impact of physical risk on the NAV across, for example, a number of sectors by 2050, I see something interesting. I see that the mean is 4.4%. So on average, I'm going to lose 4.4% of my NAV because of physical risk, which sounds like not a lot. But actually, if you look at the details in different sectors, it's quite different. Of course, different assets are exposed differently to those risks. And as you know, we have this extremely granular view on how those risks correspond to each asset. For example, in transport, it's higher. On average, we're going to lose close to 11% of the NAV by 2050. On average, for all infrastructure, for all transport assets, right? In water and natural resources, 7.5% of loss. So these are already numbers that start to look a bit concerning. But that's the average. The minimum remains very low. Why? Because even in this really this hothouse scenario with more physical risk, some assets remain pretty much scot-free. They are in places where it never rains and doesn't get too hot, and so nothing much happens to them. But some assets get bashed really, really badly. So this is the maximum number that we get across this entire population. So this is the most impacted asset in each sector, and the maximum number is close to 27%. On average, and in some sectors, you see it in transport, we have an asset that's basically going to disappear, 97.8% loss in NAV, so gone. But again, you're out of business long before you've lost 97% of your NAV. On the DCF basis, you're defaulting and going out of business long before that. In the water and natural resources sector, we have minus 40% loss in some cases, meaning again that you're pretty sure to be already in default at that stage. So quite significant numbers, but again, quite also different across sectors. All right, so that starts to be quite interesting. We see that physical risk is pretty material, and there are multiple channels through which physical risk is going to express itself in infrastructure investment, through the cash flows and through the risk premium. We see that by 2050, on average, across a very wide population of assets, this is limited, okay? It's not Armageddon, but it remains highly idiosyncratic. In other words, it's very variable between assets and also between sectors. And in some cases, it can be very, very high. So that could be a concern for some investors. It's very possible that some investors are highly exposed to these risks already, and increasingly so until 2020. So in order to picture this a bit better, we have a final exercise, because no one invests across 700 assets. So no one has that level of diversification. And I call it diversification, but it's a bit of a misnomer because it's all downside, right? Diversification means you win, you lose, you win some, you lose some. There's losses and gains are partly offset each other. Here it's all downside. You can just limit it by having some assets that are less exposed than others, limit it on average. So to try and understand better how that really looks like for an investor that does not invest across 700 or more assets, we did an exercise which is called the climate roulette, which consists of doing the following thing. First, we look at how many assets on average do investors have in that portfolio. So we do this review every year with BCG about allocations to infrastructure, various investors. This is the last set of numbers we have from last year. And so we looked at 404 investors and how many infrastructure assets they had in their portfolio. And of course, this is a very variable number as well. Some have many, some have very few, but on average, you can see that it's not that many. Of course, infrastructure managers have many more than the others. This is per investor, right, or per manager. So this would include several funds. But managers, that's all they do. So they have more assets, of course. Multi-asset managers that don't just do infrastructure, but are asset managers also have more assets in their portfolios. But direct investors tend to, so sovereign wealth funds, pension funds, insurance companies that invest directly in infrastructure, not via funds, or at least in this case, we don't count their fund investments when they have some. It's just their direct assets. Have very few. Okay. So even if we assume that these portfolios by type of investor are going to be equally weighted, which they are not. So usually you have 8 assets, and 2 of them make 75% of the portfolio. But let's not talk about that for now. Let's assume they're equally weighted. With that number of assets, you still have each asset represents a significant bit of the portfolio. Right? So if one of those or 2 of those is an asset that is exposed to physical risk before 2050 in the way that we just described, this might be interesting. Anyway, so this is the input to look at different types of portfolio. And then what we do is very simple. We have these hundreds of assets. We've computed their pure physical risk in this hothouse scenario. Now we're going to build thousands of random portfolios with between 5 and 20 assets. So now you know why we pick those numbers, because these numbers are representative of typical number of assets in the portfolio of an investor. And again, so we would just take anything in the database randomly, and we make many portfolios with 5 assets, many portfolios with 6, 7, 8, 9, until 20. And we just stack up the losses that we've already computed because of physical risk. Incidentally, as part of the broader exercise, we've also done this for decarbonization scenarios, below 2-degree scenarios, where we don't take into account physical risk, but we take into account carbon emissions and carbon taxes. So for the sake of comparison, I've added another set of data here, which is the same calculation with the pure effect of transition risk compared to the pure effect of physical risk. And here you can see, so let's look at physical risk first. You can see that if you have very few assets, so this chart shows you the maximum portfolio loss. Okay, obviously, in those portfolios with 5 assets, you can have anything. You can have 5 assets that have 0 exposure to climate risk, of course. But you can also have 5 assets that have a lot of exposure to climate risk. In this case, in the maximum case, the maximum loss we see is about 50%, 54%. So hence the headline of our paper. If you have only a few assets in your portfolio and you're a bit unlucky, you maybe way down the loss scale. Okay. Of course, if you have more assets, then you start to diversify, or at least dilute your physical risk. So I think it's probably a better term, the dilution rather than the diversification. And so you have less maximum loss. But even if you have 20 assets and you just happen to have the wrong ones, your maximum loss is pretty high. It's 27%. Okay. So in all cases, in the most unlucky, perhaps, case, physical risk can have a very dire impact on your portfolio before 2050. And another interesting comparison is that if we were in a world with decarbonized world with no physical risk, but the cost of transition, these numbers, these extreme numbers, are much lower. They also are. So you also can lose a lot of money with the transition if you're very exposed, etc. But you lose, in extreme cases, you lose a lot less, twice as less. Okay, so that goes to show that being on the path to decarbonization, even though it's costly and still includes, in some cases, high risk, is a much better idea than not doing anything about it. Okay. So this, and here you can see the same data but presented differently. This is just the distribution of the losses of all these random portfolios, which have between 5 and 20 assets. And as you can see again, so of course, many of those portfolios have losses that are more like between 20% and 0%. This is not the extreme loss anymore. There's all the losses, right, of all these portfolios. Many assets would have losses that are in this area, 10, 5, 20% by 2050. But the maximum is extremely high for current policy scenarios. And again, for a more decarbonized scenario, it's much less high, even the maximum loss. So there goes the proof in the pudding, if you want. You can have very high losses due to physical risk before 2050 if you happen to be exposed to certain assets. Now, these risks are not well documented today. We know that. I've showed you why. And so some investors are lucky and they have low exposure, but some investors may not be so lucky. Do you know what's in your portfolio? Do you know how exposed you are to these risks at a very granular level? It's a good question, because it's not that kind of roulette. It's not the roulette where you win some and you lose some. It's more like that. If I may make this comparison. Okay. Right. So to conclude, what have we learned? It is getting physical for infrastructure, and you shouldn't underestimate the importance of physical risk in your infrastructure portfolio in the next 30 years. On the contrary, and the way to go around this and to manage this is first to measure physical risk. You can do it with great precision for infrastructure assets now if you have the right technology. If you combine this with an asset pricing model, you can come up with a dollar value for your physical risk. It doesn't need to be a color in a table or a score, right? That is a bit useless. And even if you have conservative assumptions, because as I said, the hot house scenario, the current policies and the FS scenario are not that crazy, they're not that bad. you can still find a very high risk for a growing proportion of the assets, especially in the most concentrated portfolio. But in any case, all portfolios face high extreme losses. It's very rare that the portfolios that are completely immune from this are extremely rare. So everybody should be worried about this to a point, and in some cases, a lot. And then the answer to my second question, of course, is that because all this infrastructure is in developed economies, and I showed you the list of the countries at the beginning. Well, there you go. In developed economies, you can have these kind of things. It's not necessary to invest, or it's not necessarily come hand in hand with investing in other markets to be exposed to physical risk. It can happen anywhere effectively. An important conclusion for me is that you can measure these risks, therefore you can manage them. So you should measure them probably. But first, yeah, they need to be documented. And I hope today you've learned a little bit about how it can be done. All right. So that's me for today. I think I've used a little bit too much time, but thank you for your attention online and offline. Is there a couple of questions I should be looking at? If we still have a few minutes. Any questions in the room? No. So let me just look at some of the questions that were asked. So a question, okay, the estimated loss is in today's value. A question from Calliope. Yes, it's discounted back to today. Is there a way to estimate the loss in the future? Yes, you could, but we calculate the value in the future, but then we compare it with current values. But it's possible, yes, but actually I think it's more useful discounted, but that's where we can actually compare the assets. Question from Will: do we need to reassess what defines a 1 in X year event, since they are all getting much more frequent? Does your model account for that, or have a mechanism to adjust for it? So the answer is yes. We need to reassess any 1 in 100 year event today in the future, depending on the scenario, depending on the evolution of global temperature. What we do is exactly that, is to account for this evolution. Otherwise, we would not be looking at future risk. We'll be looking at, again, at the baseline. So yes, we absolutely allow for the reevaluation based on what we know the evolution of the risk will be. We reevaluate the 1 in 100 year event, and as I was saying, by 2050 it actually becomes a 1 in 50 year event. So there's lots of questions, so I'm not sure I have time to answer all of them because I've already gone over them. A question from Sophie: when looking at the effects on OPEX, total debt, revenues, etc., how did you exactly quantify this? Did you use historical data on the assets where a scenario may have occurred before? So that's an important question. We quantified the effect by creating a model or a regression model of the relationship between historical financials and things like GDP, inflation, interest rates, etc. So a kind of macro betas, if you want, of total assets, revenues, etc. Which then allows us to project these numbers in the scenario, because these scenarios consist of GDP, inflation, interest rates, etc. of quantities. So it's calibrated with historical data, but using the scenarios as predictors. How do you reconcile discrepancies between desktop data prediction and the actual on-the-ground conditions, which might differ significantly from the model's prediction? A question from Richard. Yes. Well, yes, as I was showing with the Italian example, there's the flood model and there's the actual flood. But in the scenario, we only look at the flood model because we don't know what the actual future floods will be. The point of what I was showing is that when this happens, well, first, we can actually measure what happens quite well, given what happens. That's the point of this, prove the approach, the validity of the approach. Then the question of what actually happens is, again, more of an insurance question. Once it's rained, how much does it rain? How much damage is there? How much is it going to cost? It's not really a climate change risk question. So we only look at what models say that will happen with 1% or 2% probability in the future, but not that we don't predict rainfall. We look at the possibility of rainfall, the possibility of storms, etc. All right, I think that covers the time for today because we're already way over. But thank you for your questions. We'll try and answer all of them in writing in the next couple of days. And it's time for me to say goodbye and to thank you for your attention. And thank you everyone online. I think there was many hundreds of you today. Goodbye.